Engineers often need to create and simulate models of real-world components and systems in order to predict their behavior. A common way to do this is to start with a block diagram, which is a visual representation of system components, their underlying math, and the connections between these components. The next step is to move from the block diagram to simulation. That's where Simulink comes in. By connecting and grouping blocks, you can model components and algorithms. You can then simulate your model just by pressing Run and inspect its behavior with various readouts. The graphical layout makes it easy to model systems like this motor controller, or even an entire aircraft. If this looks complicated, don't worry. In this course, we'll walk you through modeling dynamic systems from the very beginning. We'll learn about adding and customizing blocks, integrating custom MATLAB functions with Simulink, creating filters, and representing dynamic systems. Finally, you'll apply your knowledge with some projects. You'll implement the logic for an automotive performance package, model a thermostat, and capture the dynamics of a diving peregrine falcon. Since Simulink is built on top of MATLAB, it will help to have a basic familiarity with the language. If you've never used MATLAB before, it's easy to get started. We recommend you first take MATLAB on-ramp to get you up to speed quickly. It's also helpful to have a working knowledge of ordinary differential equations. Don't worry, we won't ask you to solve any, but we will model them. Throughout this course, you'll be completing tasks in the Simulink editor. It's the same Simulink editor you'll encounter outside of this training, but with a few added features on top. In particular, each task will have one or more assessment blocks. These blocks are unique to the training environment and provide you with feedback when you submit a task. Depending on the type of block, they evaluate either the connected signal or the overall properties of the model. And with that, you're ready to go. Let's get started. As you've just seen, Simulink scopes allow you to monitor signals in your simulation. Just like an oscilloscope, you can monitor signals while the model runs, as well as record data for further analysis. But scopes do more than just plot outputs, so let's take a look at what else you can do with them. You can inspect a signal in more detail using the zoom tools, including independent axis zooming. The pan and autoscale tools also help you find what you're looking for. The scope display is customizable from the Configuration Properties menu. From here, you can choose to automatically open the scope with the model, or save the scope data to the MATLAB workspace. You can also adjust the layout of the scope, for example, putting each signal on a separate subplot. Or, as we did in the previous exercise, use a single plot with a legend. As a reminder, legends take the name of the signal connected to the scope. Simulink's Run and Step buttons are also available directly from the Scope tool strip. Stepping through a simulation can give you insight into what's driving the behavior of the model, and it's a useful troubleshooting tool. You can make common measurements on the signals from the Tools Measurements menu. If you have toolboxes other than Simulink installed, you may see additional menu items here. The cursor measurement window allows you to trace signals and estimate the period or slope between 2 points. If you want to share your simulation results with others, you can export the scope images using our print and copy functionalities. The Copy to Clipboard option adjusts the colors of the scope image to make it appropriate for including in other documents. If you want to know more, use the Scope's Help menu to access the Scope documentation page. Engineering is full of dynamic systems. Dynamic systems have states whose values evolve over time. A state is just a type of quantity, like position or population, that depends on previous states as well as other properties of the system. For example, states depend on the initial conditions, physical characteristics of the system, and any external inputs. System outputs, in turn, are dependent on the states. Dynamic systems can be discrete or continuous. With discrete systems, we monitor the states at specific time points. The dynamics are described by difference equations. The current state typically depends on the time history of one or more past states. In some systems, we model time as continuous. In other words, for that case that the time between samples approaches zero. Since we assume infinitesimally small time steps, continuous dynamic systems are described by differential equations. Computationally, we keep track of the derivative of our state instead of the state itself and integrate at each time step. In Simulink, signals carry the values of states, like position or velocity, inputs, like gravity, and outputs over time. As always, blocks allow us to express the relationships between these signals. In the next lessons, we'll learn how to express the relationships to model dynamic systems.